Okay, section 6.6 begins on page 333, although we're not going to look very hard at that page, but that's where you first see it. And it's called solving. Now we're going to take equations that have exponents or logs in them at the beginning of it and follow a process to actually get at the very end x equals some number. And because most logarithms are irrational, you're going to need to calculate it and do these at the end. You need to show your work and how you're going to get to the end before you actually calculate anything. It should not be the first thing you pick up. First thing you should pick up is your pencil and do some things with it. Anyway, I'm going to show you how to do it, give you some examples, talk your way through it, and then we will turn you loose on it, see what you can do. It's interesting. Do you remember the skill right at the very beginning where you change logs to exponents, or you change an exponent to logs? This is where you got to know how to do it. If you don't know how to do it, you're not going to be able to do it. Because if an equation is offered to you as an exponent, where the variable is in the exponent, you cannot touch it without a logarithm to bring it down where you can access it. When it's up there in its little ivory tower up there, or serving as an exponent, you cannot get at it algebraically. So you have to change it to a log to make the x part of it even accessible, and then work with it from there. And if you have something that's offered to you as a logarithm, like you have log base 3 of x equals something, you have no way to access that x behind that log because logs are exponents, right? And so you have to change that log to an exponent before it becomes something you can deal with. So you have to be able to change from one to the other to even begin to tackle equations that have these things. So the very first thing that they do on page 334 is tackle the idea of having an exponent with the x in the exponent up there where you can't get to it, and you have to solve it. So here we go. The very first equation is 100 to the x. There's that x that's inaccessible algebraically, and there's another one, 1 over 10 to the x minus 3. Now, all that talk I just told you about, you could change both of these to logarithms, by the way. But all that talk I just told you about, because these two things, this 100 and this 1/10, they are both powers of 10, we're actually going to handle it a little bit differently. If the bases of your exponents have something in common, you're going to handle it by writing them with the same base. This right here, if you notice that both of these could be written as 10 to the some power, both of these, then you should do that. That would be 10 squared raised to the x. All I did is rename 100 as a power of 10. You with me on that? Or not? Yeah? Okay. And then I'm going to rename this one as a power of 10. Looks like that. You should be comfortable with that. Right? 10 to the negative 1. So that's another name for 1 over 10. So all I've done in this step is rename the 100 and rename the 1/10 as powers of 10. That's still to the x minus 3. And then we apply a property of exponents, which is if I've got 10 squared raised to the x, that's 10 to the 2x. Because when you're powering a power, you multiply, right? Okay, same thing over here. It's going to be 10 to the, now think about this, it'll be 10 to the negative x plus 3 in the distribution of the negative 1. You see it?
Yep.
All right. This next part is not algebra. It's not math. It's not transcendental math. It isn't math. It's reasoning. I want you to think about this. If you have 10, the number 10 raised to something, and over here 10 raised to something else, if those two things are going to be equal, don't the somethings have to be equal?
Yeah.
If you've got 10 to the third, it does not equal 10 to the fourth. 10 to the third equals 10 to the third, or whatever. So if 10 to something equals 10 to something else, the somethings have to be equal. And this is not a math step. The 10s don't cancel. We don't drop them out. I mean, we do drop them out, but they're not going to cancel. It's not something we divide out or multiply out or factor out or anything. It's nothing like that. It's reasoning. 10 to something equals 10 to something else makes the somethings equal. And that's your next move. And then it becomes a nice linear equation that you were taught to handle in Algebra 1. So we add this x over to here. We get 3x equals 3. And lo and behold, x is 1. You should check that out. 100 to the 1, that's 100. This is, if I put a 1 up here, 1 minus 3 is Negative 2, and 1/10 to the negative 2 is the same thing as 1 to the negative 2, which is 1 over 10 to the negative 2. And isn't that 10 squared?
Yeah.
Which is 100? So it works. Takes a little thought process to make sure that it does work, but X does. When you plug it in there, it works that way. So if you notice right at the beginning of the presentation that you got X in two places, and they're both in exponents, it's very likely that they will give you the bases of the exponent that are related by something, in this case 10. Okay, did you follow that? And then right when you get to this step, you got to reason your way into this equation here. Nothing canceled, nothing mathematical happened. It's just that this exponent has to equal this one if 10 to it has to equal 10 to it. Okay? Next one. 2 to the x equals 7. This one isn't, this one I'm demonstrating isn't like this one. 2 to the x equals 7 is not like that at all. First of all, you don't see any 10s in both of these. You don't see anything that's common at all. 2 and 7 are both prime. They have nothing to do with each other. Also, you notice that we don't have two exponents. We have just one. That's where changing to a logarithm is very helpful. So if I take x log 2, but base 10 log 2, because I want to use my base 10 key, x log 2 equals log 7. What I did is I logged both sides and at the same time applied that exponent property you practiced yesterday. In logging it, I brought the x down. Now the x is accessible algebraically. All I got to do is divide by log 2. Here's what you got to get used to. You got to get used to the idea that this very strange expression right here is just a number. You may not know, but your calculator does. So it's x times a number equals another number. How do you isolate x? You divide by the number that's being multiplied by it. So x is going to be log 7 divided by log 2. And then and only then do you pick up that calculator once you've got it to here. It knows both of those values, and all you got to do is make sure. Here's another thing that happens, folks. When you put this in your calculator, you put log, and it automatically slaps down a parenthesis. If you put 7 without looking up at your screen and then divide it by, it's going to divide inside this log. It's going to divide 7 by log 2. And that is not what you want. That's why it's very, very important you make a habit of closing off all your logs before you do anything to them. That's what you want. So you have to close off that 7. Otherwise, you've got a log within a log, and that's not, it'll calculate something, it'll be wrong. What do you get? To the nearest, let's say, 3 places.
2.807.
Heard about your homework. What do you get?
2.807.
Now think about that. Isn't 2 to the 2 4? And isn't 2 to the third 8? So doesn't this make sense? It's closer to 3 because 7 is closer to 8, but it's still less than 3. Y'all see it? So you should kind of look at it, make sure it makes sense to you. So in one case, we had x's in 2 places with the same, that could be forced into being the same base. That's an interesting situation. But over here, we had one exponent, and the bases of these 2 things, of this base and this thing that it's equal to, had nothing to do with each other. That's when you use the change to a log thing. Did it feel like we changed to a log, or did we just log both sides? We kind of just log both sides. Could you have changed that to a logarithm and figured it out? Let's see. Let's see if we could actually change this to a logarithm rather than logging both sides. By the way, both strategies are okay. I'm not going to have much room over here, but I got to stay in the window. Ooh, I'm not in the window. I'll come over here. 2 to the x equals 7. Let's try the other strategy so that you understand what you've got available to you. How do you change this to a log?
Log a base of 2 of x.
Of 7 equals x. Try to remember that changing this to this is a process for isolating x. So if you can't remember where the 7 and the x go, that x has got to be isolated in this move. That's what it does. You know what I'm saying? And then you remember your change of base rule from yesterday too? This thing right here is the same as log base 10 of 7 divided by log base 10 of 2. Remember that? Log of the big guy over log of the little guy. If you use base 10 log, remember that big change of base rule? Yeah. And isn't that just what we got by doing that? So either way it's going to work. You change your exponent to a logarithm, or just log both sides. It will result in the same quotient. You following? Got 2 different ideas there? Okay. Let's take a look at example 3. We're still dealing with exponents, an exponential equation. Here's an interesting thing that will always show up in any time you're discussing or talking about exponents and logs. We'll always come up with this thing called Newton's law of cooling. It's an interesting thing, and it's a variation on this, so listen carefully to how it works. An important application of exponential equations is Newton's law of cooling. This law states that for a cooling substance, a substance that's too hot, and you leave it on the counter, it starts to cool, with an initial temperature, and we pronounce that T naught. It means T sub 0 means the beginning. The temperature at the beginning of, and we start, because we're going to clock it. What we're going to do is we're going to start a stopwatch, and we're going to wait for it to cool. It's going to drop down to temperature, and when we start it, the temperature at the moment we start the timing is T naught. The temperature, capital T, is changing all the time. Like if you take a cake out of the oven or a pie out of the oven, you put it on the counter, the temperature of that pie is constantly changing as it approaches room temperature, right? And so that's capital T. It doesn't have a subscript on it. That T is always changing. T naught is the temperature. Take it out when we start the clock. And little t, I know it's all a bunch of t's, but little t is important for the cases on this. Little t is the time in minutes in this case. And here's what it says. The temperature of the pie, we talk about the pie we took out. The temperature of the pie is equal to the initial temperature minus the temperature of the room. That's what our TR stands for, is the temperature of the system. That'll stay constant while it's cooling. That difference times e to the negative RT, little t, plus the room temperature. You have to add that on too. And the only thing that we didn't describe is what that little r is, that little piece of the exponent, negative RT. Well, I'm here to tell you that little r will have to be given to you most of the time. Sometimes you have to find it. That's an interesting thing. But I'll show you that in a minute. But that r is a decay. It decays the temperature from something really big to something smaller to come down. And it's different for every substance that cools. It will be different if you take a pie out of the oven than if you take, I don't know, a piece of ice out of the freezer and let it warm up. This still applies to things that warm. It's different for human tissue. After a person's dead, they take their liver temperature, and there's a certain R value for human tissue. And it's different. That's different from a popsicle that's cool, that's warming, or a piece of metal that you finished welding that you put in the bucket. The R value is different for the substance that's cooling. You with me? And they will usually tell you what it is. And if they don't tell you what it is, they will give you everything else and ask you to go find that particular decay value. Okay? So here's our situation. You are cooking a leche. I think that's what I said. A leche. An Ethiopian stew. When you take it off the stove, its temperature is 212. What have they told you?
They told you your T naught.
T naught, right. I'm going to erase this so that I can write it up here and stay on camera here. So just a minute, I should have erased this first. So in that very first instance, you need to figure out what they told you. They told you this, and you just keep track of your information. The room temperature is 70 degrees. What is that? T sub capital R. You just keep track of your stuff. Write it down on your paper when you do this, so that you can put everything in where it goes without having to hunt through the words again. And the cooking rate over the stew is R equals 0.046. See, they gave it to us. Little r for this stew is 0.046. And that number will be different if it's just water. It'll be different if it's milk. This is really, really gross, but did you know that we're talking about boiling things here? Did you know you can't boil blood? You ever tried it? Because you probably have seen this. If you're frying a solid piece of meat, generally a solid piece is easier like a steak or something. If you're frying that in a pan and the fluids begin to come up to the top and they spill off and hit the pan, the heat of the pan, it turns into that gray, gooey substance. That's because it coagulated. The same thing happens when you fry an egg. That the whites at a certain temperature will thicken and coagulate because of the substance that's in them. And if you've got a pot of blood, it may boil as it's losing some of the water, but it just turns into that gray substance. It's really gross because of coagulation. has nothing to do with this, I studied that. Okay, so we got stew, okay, and we've got the R value. The question asks, how long? What are we looking for? Little t, they're asking you for a time unit. How long will it take the stew to cool, to cool the stew to a serving temperature of 100? So what is that 100? That's what we want to arrive at before we put it in bowls to serve up. But what variable in our equation is that? Which T? The big T. Yep. The temperature that continues to change. That's the one. When that one right there that keeps changing as it cools goes to 100, that's when we want to serve it up so it doesn't burn people. Probably don't want to serve it too much later than that because nobody likes cold stew, right? Okay, so T, we want to arrive at 100. What do we want to find? Which of those variables? Little t. So it's kind of important that you summarize things as you read through it so that you've got all the things that you need. Then we take Newton's law of cooling. And by the way, you won't have to memorize that. If they have a Newton's law of cooling thing on your test, they will give you the formula, which is T equals T naught minus TR in parentheses. It's capital R. E to the negative RT plus T sub R. So here we go. This gets replaced with 100. T naught is 212 minus the room temperature, 70. E to the R they gave us is, and notice that it's 0.046. This has a negative on it, so you have to put a negative on it. This would be a positive number if you were warming something up. If you pulled something out of the freezer and it was warming up, this would be positive. That's the difference. This one's cooling down. This thing, this T right here is getting smaller and smaller and smaller, and this is what makes it happen. The negative, okay? T, we don't know, little t, but we do know TR is 70. We okay so far? Okay, now we got to go after that T. We got to do it very carefully. You cannot change anything to an exponent like we did over there. I mean, exponent to a logarithm. You can't log both sides or anything like that until you get this chunk that has the T in it, until you get that piece all by itself. So we got to get rid of the 70 first by subtraction, and then we got to get rid of this difference by division. Do you understand? You've got to do some algebra on this before you can apply any of your exponential rules. So the first thing I'm going to do is get rid of the 70. I'm also going to do this difference. So I have just a single number there. What is it?
142.
Sorry?
142.
142. E to the negative 0.046t. Got one more thing to do. I got to divide 30 by 142. And I know that will reduce, but I don't care that you do it at this point. You can do it when it'll reduce and work out no matter what, whether you reduce it or not. So I'm just going to leave that. My objective is to isolate this. You can reduce it if you want, but it's not necessary right here. All right, so we followed the algebra that we know to get this piece that's got the t in it all by itself. Now we've got two choices. We can log both sides, like I showed you before, the one I erased there, or we can change this thing to an exponent. My preference is always to log both sides. Is that okay? All right. So, and this is interesting too. Before I do that, can anybody tell me what, gotta stay on camera here. Can anybody tell me what this value is? The log of 10. What is that? The log of 10. What is it? 1. Here's why. Look, remember this is log base 10? Remember that? When you have a log base 10 and an exponent base 10, they cancel each other out and leave you only with the exponent that's right there, which we know is 1. Right? What's the log base 3 of 3? 1. What's the log base 19 of 19? What's the natural log of E? 1. This is log base E of E. You with me? So the reason why I went through this process is because when you've got a situation an exponent base E, you want to use natural log. Because eventually you're going to be logging E, which is a 1. And that makes things really nice and neat. You don't have to use your calculator if you choose the correct log. If you've got a log base E or a log base 10, you should use the button that's already built into your calculator when you log it. I could use log base 10 on both sides. but it'd have more calculations, more opportunity for error, and it would be a little bit longer. Because this is an e, I want to natural log both sides. I'll show you why. It'll show up right here. When I log this, the natural log this side, it's going to be negative 0.046 t. Natural log of e, see how that just goes to 1? That's nice. If you choose the right logarithm. So that went to 1, and I've only got one step left, and that's to take the natural log of this fraction over negative 0.046. Before you do that, put your calculators down for a minute. I want you to think about this for a minute. Is 30 over 142 more or less than 1? Less. Do you remember what the log curve looks like? It looks, if I put the one, any log curve, by the way, that hasn't been embellished at all, or hasn't been moved around, or whatever, will always cross. I'm going to put it way out here so that you can see it. This is a 1 right here, and the log curve will have hugged this really tight back here. As it comes up, it'll cross right there and go out that way, right? So anything in this range of values, that would be proper fractions, wouldn't it? From 0 to 1. Any number that's in here would be a proper fraction or an irrational number less than 0. Well, I'm talking about proper fractions here. Any x value that falls within this range right here is going to have a negative y value. Do you agree? The only reason I bring that up is because we are logging a proper fraction. 30 over 142 is somewhere in here. It's got a negative value. So what I have here is a negative number divided by a negative number. That should make you happy because we need a time unit that's in the future. That always bothers people. They go, well, we can't divide by negative because time can't be negative. It won't be because you're logging a proper fraction, and that's a negative number. Just something to note and observe. This is a negative, divided by a negative will give you a positive. It's important to know that. It'll become more important as we go along. So anyway, now calculate that and make sure you close off that parenthesis before you put negative 0.046. Tell me what we get for a time unit. Oh, then there's 10.
All right, 30, yeah.
What?
33.8
And what's it measured in?
minutes.
Minutes. I tell you what, I never wait that long to serve up my stew. But people generally, when I serve up soup, or especially if I give mashed potatoes or something to Allie, I make sure I'm blowing. That accelerates this whole thing. You know, don't want to burn anybody, but you don't want to wait 30 minutes to serve it up either. Okay, so that's an example of Newton's law of cooling, and they gave you everything but one thing, and then you got to go after it. You got to isolate this before you do anything we've learned in this chapter. Okay, moving on. Take a look at example 4. Uh-oh, now we've got logs to solve. So everything we've done so far, the equation has been presented with the thing we want to find in the exponent. So those were exponential equations. And we ended up solving those by eventually logging both sides. Okay. This one's a bit more restrictive on your options for solving this logarithms. You still have to isolate the log. You have to get it by itself algebraically, like we just did with the stuff I just erased on the law of cooling. But then you have to change it to an exponent. So here we go. The A part says find the value of this equation. Natural log 4x minus 7 equal log of x plus 5. Okay, even though this one particular one is a natural log or is a logarithmic equation, we're going to use the exact same notion we did when we ended up with this, when we had 10 to the 2x, remember that one, equals 10 to the, I think it was negative x plus 3. Remember that? When we got to that point, we said if 10 to something equals 10 to something else, the somethings have to be equal, and we reasoned that out. The exact same thing is true of logs. If the natural log of this is equal to the natural log of this, the thises better be equal, so that when we natural log them, they'll be equal. Does that make sense? Here's how you recognize that reasoning idea. There's a log on both sides. On this one, we had an exponent on both sides that had an x in it. When that happens, then you can reason it out. If this were natural log and this were common log, we couldn't do it. Just like if this were 10 to something and this were 8 to something, we couldn't do it. It has to be the same base on the exponent, has to be the same type of logarithm. But if it is, then you can write this and it has nothing to do with canceling. Get that out of your head. It has to do with reasoning. If the log of something equals the log of something else, then the somethings are equal. That's a reasoning step. No algebra in that. Then you solve it like normal. It'll be 3x equals 12, x is 4. Did you catch that? Okay. Sure enough, 16 minus 7 is 9, and 4 plus 5 is 9. In both cases, you'll be natural logging 9. So that is the value of x that makes it happen. So if you got a log on both sides and they're the same kind of log, then you can take the things that you're logging and set them equal to each other. But it's not a canceling move. Don't think of it that way. It's a reasoning move. Okay, here comes the next one. Another log equation. This one has only logs on one side. That means that we're not going to use this strategy. We've got log base 2 of 5x minus 17 equals 3. So that's different from this one because this had a log on both sides, so we just dropped them. Dropping's okay, but canceling, using the word canceling is not a good idea. We dropped the logs in favor of this. That's not what we can do here because we only got one log. But since we have one log, we can change it to an exponent. That's what you got to do to get at this stuff behind the log, to get it isolated where you can deal with it. You're going to have to change this log to an exponent. What would it be?
2 cubed equals 5x minus 17.
Can you do the 2 cubed in your head?
6,
8 is equal to 5x minus 17 because 2 raised to the third, that's 8, is equal to this stuff for logging. See it? See how clean that worked out? This is now an algebra 1 problem, one you can all handle. Changing the exponent to a log did that. So we add 17 to 8, we get 25 equals 5x, and so 5 is x. Now, there's always a big but in these things, it seems like. Remember, do you remember the 3 things in high school algebra that cause domains to not work? X values to not work. You can't, you can't divide by 0. That has to do with denominators. This doesn't have any denominator, so it's not that. You can't log a non-positive. You can't even log 0. And you can't square root a negative. Those 3 things cause problems. Since our equation began with one of those problems, you have to check this to make sure it's going to work. So what we do is we plug it up in here and we say, okay, 5 times 5 is 25, and 25 minus 17 is 8. So now what you have is this, the log base 2 of 8. What is that value? Remember your change of base rule? You log 8 divided by log 2? 3, which is what we wanted, so we'll keep it. It did work. But you have to check it. Especially, you can tell without having to plug in your calculator, if when you plug this in here, you get a negative number, you can't log a negative, ever. And so you throw it out and say there's no solution. Yes?
So how'd you get the 8, the second step?
Oh, sorry, I did skip that step. It's taking this base, remember, to change this log to an exponent, you take the base raised to the other side equals this junk you're logging. That's where the 8 came from. 2 to the third is 8. Do you see it?
Yep.
Okay. We just did the arithmetic in our head as we did it, and we missed the details. So. What? It's fine that you're talking. Please talk until you understand it. Is everybody okay? You don't need to stop just because I'm looking at you. I'm waiting for you to finish. Everybody good? Yeah? Okay, good. All right, let's try another one. Example 4. Oh, example 4 is where we put a wrinkle in things that's going to cause people a little bit of difficulty. Not a lot, if you remember what you learned yesterday. So, we have log 2x. And even without parentheses, that means log 2x. I mean, if they wanted you to do log 2 and then multiply that times x, they would have written this. Like that. When the 2x, both the 2 and the x are following it, it means we're logging the product 2x. You can put parentheses around it if you want. They didn't, but it's the log of that plus the log of this difference, x minus 5. That does need parentheses because it's unclear where that 5 goes. Equals 2. We wish to solve that log equation. And the only strategy we have, if there's not a log on both sides, the only strategy we have is to change it to an exponent. But you're not ready to do that because you got 2 logs on the left. How are we going to make them 1? Yeah, by condensing. You learned that yesterday. You got the sum of 2 logs? Make it the log of that product. Remember? So we're going to condense this expression by what you practiced yesterday. And that's going to be the single log of 2x times x minus 5 because products or sums become products when you condense them. Remember? You see this move from here to here? You practiced it yesterday. And if you didn't practice it yesterday, then this problem will make a lot of sense. But if you actually practiced it and got them right, going from here to here should make a lot of sense. Are we good? Equals 2. It's just a rewriting of this. Now we have a single log. That's the objective between teaching you that stuff, is when you go to solve these things, sums and differences of logs can be chunked together into a single logarithm, and then you change that log to an exponent. How do you change this log to an exponent? What would it look like? Look at what we did over there, right? Going from this step to this one, and do that to this.
100 equals 2x parentheses x minus 5.
Do you want to distribute that as you go?
2x squared minus 10x.
Okay, we did a lot of arithmetic in our head there. And he's correct. But if you want, I can slow it down and show you where it all came from. Would you like that?
Yeah.
Anybody need that? Okay. Hope that step will show up in just a minute, but this is the intermediate stuff. Remember what we did over here? To change it from here to here, we took this base raised to this power, right? Well, what is this base? 10. When it's not written, it's 10. So it's going to be 10 to the 2. That's where the 100 comes from in the next step. 10, that understood 10 right there, raised to the 2 equals this stuff that you're logging. Just like we got the 5x minus 17 over there. It's 2x times x minus 5. Catch that? Everybody follow? That understood 10 right there is not written, but you got to know it's a 10. If you want to write it, you can. That's fine with me. 10 raised to the 2 equals this stuff we're logging. Just like 2 raised to the 3rd equals this stuff we're logging. See it? See how they're the same? And then he did this in his head. 10 to the 2 is 100. He wrote that down as he saw it. And he also distributed this, which is 2x squared minus 10x. You okay? Okay. Now we subtract the 100 to the other side. Why do we do that? Because what we have now is a quadratic. And the way we handle quadratics is to get everything on one side where the squared term is positive. Right? All right. Can't forget all your other skills. At this point, in order to find x, what are your options? Quadratic formula. Factor it. Those are 2 things you can do on paper. What else? Graph it. Polyroot find it. Yeah, you got those 4 choices. 2 are electronic, 2 are on paper. I don't have my calculator out right now, so I'm going to see if I can do this on paper. You can use electronics if you want. First thing I'm going to do is factor out a 2. Next thing I'm going to do is recognize that factors of 50 that subtracted 85 are 10 and 5. Oops. Ten is negative, 5 is positive. This 2 out front doesn't count because he'll never be 0. And yet, x is either 10 or negative 5. You'll get that with your polyroot finder, by quadratic formula, or any of those other methods. That's what you'll get if you don't make any mistakes. Everybody clear? Both are options for x. We have to check them. Where? Not in any other previous step. You must go right to the original. So if it's going to be 10, what I want to know is the log of 20, because it's 2 times 10, is the log of 20 plus the log of, that would be 10, log of 5, Is that equal to 2? Check it out. Take plus the log of 5. No? Doesn't work? Did I do that right? Oh, sorry. This should be 20 because I'm being silly. Try it again. It should have been 2 times 10, not just 10. Sorry about that. That's what you get for plugging it in wrong. That's 2. If you do it right, you get it right. Yeah, okay, so we'll keep the 10. Now, if you go to plug negative 5 in there, the very first thing that happens is you'll be logging a 2 times negative 5, which is negative 10. You're logging a negative right there. You can stop right there and reject this. X equals 10 is the only solution. Now, people, I need you to understand this and listen to me right now, very carefully, because it's going to happen so often you're going to think it's a fact, and it isn't. We did not reject this negative 5 because it was negative. That is not why we threw it out, because some negatives actually work. Some positives actually fail. We did not keep this because it was positive and throw this out because it was negative. That is not why we did that. We kept this because it worked out and gave us a 2. We threw this out because it caused us to log a negative in one of these 2 things right here. Not because it was negative, but because it caused us to log a negative. You will have to give an explanation as to why you rejected something on your next test. And it is not because it was negative, because it made us log a negative. You with me? Some negatives actually make you log a positive, in which case you keep it most of the time. So you have to check these out in the original equation. And logging a negative, an answer that causes you to log a negative is one you throw out. One more thing. Okay, no, 2 more things looks like. Example 5 says solving an exponential inequality. That sounds terrible. 3 to the x less than 20 is what we want to solve. 3 to the x less than 20. So this is an exponential equation. Can you guys there see through the letter? Yeah.
Right here? No?
This is an exponential inequality. So we're going to go back to our methods for solving exponentials. How do you get that x to come down where we can deal with it? Log both sides? Okay. So we have x. By the way, get this by itself first, and it is. So it's x log 3 less than log 20. Now what do we do? Divide by log 3. But I want to talk to you about that for a minute. So as soon as you're ready, as soon as you put your pencils down, I'm ready to listen to me here. This is where that idea of that, remember that graph that I drew for you? And I said if I put the 1 out here, and so the thing came out like that, and we said that all of these in here have negative values if you're logging a proper fraction. It's important that you understand that, because at this point with an inequality, when you go to divide by log 3, you need to know whether this number is going to be positive or negative. Because if this number is negative, you're going to have to flip the sign too. But it's not. Because this is beyond the 1. It's not a proper fraction. This will have a positive value. This one will be out here a ways. 2, 3, it'll be up here, which is positive. You understand that? But of this, you have to divide by the log of a fraction. Then you're dividing by a negative, and you need to know that, or you're gonna fail to flip that sign like it should. But in this case, we don't. So x has got to be less than log 20 divided by log 30. Or log 3, and I am very sure that this sign still points left because I'm dividing by a positive. And then you grab your calculator. What is that? Negative what? Okay.
It's 2.726.
So what we're saying here is that if the x value that you plug in right there is less than 2.7 something, then 3 to it will be less than 20. Okay? Keep that. There was no chance that this would not work because this was not a logarithm. You can exponent anything. You can't log anything, but you can exponent anything. So there was no reason to check for extraneous solutions when you start out with an exponent. But you have to watch it when you start out with log. Yeah.
Can you explain again why you flip the sign?
Let's say you had something like this. you remember that when you're dealing with inequalities, if on the last step you have to divide by a negative, you also have to turn the sign over? Is it that you want me to explain?
Is that all it is?
Yes.
All right, now I'm getting it.
But if you have to be dividing by a log, like log 3 on this, if the thing you're logging is a proper fraction, like if we were dividing by log of a half, you'd have to flip the sign because log of a half is a negative number.
Yeah, okay.
You understand? Okay. But we did in this case. All right. Let's try example 6. This is a logarithmic equation that is an inequality also. So we have log x less than or equal to 2. Log x less than or equal to 2. This one's going to have a funny thing happen to it. So if you haven't been paying attention, you need to turn your attention on right now and put one and watch this. Okay, so I've got an inequality that involves a log. What do you suppose your next step is? Turn it into an exponent. We need to change the log to an exponent because we can't get at that x when it's behind that log. It's trapped. How do we change it to an exponent?
Hundreds.
10 to the 2. Let's go with that. Do y'all understand where the 10 to the 2 is coming from?
Yeah.
Less than or equal to x. So as long as x is more than 100, more than or equal to 100, it's going to work out. Is that true? It is not.
Oh, no.
It's gotta be less.
Because look, if you log base 10 100, you get 2. If you log base 10 1,000, you get 3. This 3 would not be less than this 2. So what happened? I'll tell you what happened, and you need to be very aware and careful with this. When you change this to an exponent, with this change to an exponent, it's very unclear which side you put the result on. Is it 10 to the 2 less than or equal to x, or is it x less than or equal to 10 to the 2? That's where you got to use some reasoning. Or your calculator. You could use your calculator to evaluate this. When you're dealing with logs and inequalities, it's a ticklish thing. You got to watch what's going on. Make sure that your answer makes sense. Let me show you how to handle this with your calculator so that you can make the correct decision on which way to point that thing. What you do is you graph the left side of that inequality, log x, in y1, and the number 2 in y2. Go to a standard screen. You may want to adjust it, but we'll go to a standard screen to start. Yikes. Did you see that? That's what you get, and they never cross in a standard screen, right? They don't? How far out are we going to have to go to get them to cross? 100. So go a little beyond that. Take your x's out. Go to your window and take your x max out to maybe 150. Count by tens or something so you don't get a whole bunch of tick marks. I'm going to squeeze my y's down. Did you see everything was happening really close to the x-axis? I'm going to squeeze my y's down to maybe -1 to 3 so that I can kind of see what's going on. Okay, so here's what I get now that I made that window adjustment. See, it looks like that. Now I've got a cross point. Y'all see it?
Yeah.
Guess where the cross point is?
100.
100. And what? 100 and comma 2, which is where we expected it. But look at what the question says. The log curve, at least on my calculator, I know you guys don't have a color one, but the log curve is the curvy one. It's the blue one. Okay? You see what the log curve is the blue one? When is that curve less than the line? When it's less, when x is less than 100, the blue curve is less than 2. And that's what we're after here. See, the blue curve is underneath the line y equals 2 before we get to 100. That's what we're asked to do. What could we put in for x so that when we log it, the result will be less than 2? And the answer is when x is less than or equal to 100.
You also need to put that x is greater than 0.
Absolutely. Yeah, I'm getting to that. That's a good observation. Do y'all see that the blue curve, my blue curve, is under the red curve as long as x is less than 100? But remember, we're dealing with logs. And the x also has to be more than 0 in order to log it. So when you're dealing with a logarithmic inequality, you got a lot to think about. It's not just x less than or equal to 100. You can tell from this, the curve never gets to the left of 0, so you have to ensure that that can't happen with your x's either. As long as x is strictly greater than 0 and less than or equal to 100, the log of that number will be less than or equal to 2. You see how this made the decision? When you're dealing with an inequality and a log, you better slow down. Take it easy and make sure that you understand what's happening. They've got a red and a blue curve on this, on page 337 also. So if you get to where you're logging an inequality, you can't remember the details, go back and look at example 6 and study that graph a little bit. It'll only take you a minute or two. Then perhaps you can make the correct decisions on the one you're doing on your exercise. Okay, so the moral of this story for today's lesson is, if you have the same base for an exponent, set the exponents equal. If you have the same log on both sides, set the things you're logging equal. But if you have an x exponent on one side and not the other, either change it to a log and deal with it, or log both sides. If you have a log equation with a log on one side or several logs on one side, condense them and change that log to an exponent. Then you can handle it. Watch for extraneous solutions in log equations. That's a lot of stuff in here. A lot of meat and potatoes in this section. For those of you doing it on paper, here is the assignment. Page 338, and it is numbers 1, 3, 4, 5 to 39, odd, 43, and 47 to 55, 55, odd. Okay, good luck with that. Let me know if I can help you. That's it. See ya.